You can see my screen, right?
Not yet.
Just a second. Now, can you see?
Yes, it is coming now.
Okay, okay. Okay, so welcome to the 11th week of Fundamentals of Power Electronics tutorial session. Today, we shall discuss a very important topic, which is the drive circuits of different semiconductor devices. So, till now, we have studied about different converters. We have discussed different converters. We have discussed non-isolated converters like buck converter, boost converter, buck boost converter, and we have also discussed some isolated converters like forward converter, flyback converter, push-pull converter. But irrespective of the converter, whether it is isolated or non-isolated, we have seen that we need some controlled switches, right, in the circuit. It can be BJT or it can be a MOSFET or IGBT, but we need some controlled switches. And in the beginning of this course, we saw the different kinds of devices, and we saw there are uncontrolled switches and controlled switches. We need controlled switches because we want to regulate the output voltage, right? So we need controlled switches so that we can control the duty cycle, and likewise we will get different average voltages at the output. Now we also learned that BJT, bipolar junction transistor, is a current control device, whereas MOSFET, IGBT, these devices are voltage control devices. Okay. So today we shall learn how to design the drive circuits for BJT and MOSFET. And if you know the drive circuit of MOSFET, you can design for IGBT as well. And we shall also see some overcurrent protection circuit for MOSFET and snubber circuit. Okay. So we shall discuss all these topics today and solve the numericals. So first of all, we know this is the symbol of a NPN BJT, right? This is an NPN BJT. Now for BJT, uh, this is a current control device. So we know that if you want to make the BJT on, if you want to maintain the on condition, you will have to continuously provide some finite base current. If you don't provide the base current, then BJT will be in cut-off condition, right? So, so this current, this we will call the base drive. This portion will be the base drive circuit. And how, from where this current comes, how do we supply this, what will be the supply, what will be uh, the circuit, base drive circuit, what components we will use to make this base drive circuit, those things we will see. Now, first of all, there are two transitions, right? One from off to on transition, and another is from on condition to off condition. These two transitions we already saw when we were studying about the different devices and their power loss and all these things. So we know these transitions we have to look into, right? Now, if you see from when it is coming, when it was off, the BJT was off, and now it needs to turn on. So obviously, we will have to provide the base current. And at that time, in this transition, what will be the waveforms of the voltage across BJT, the current through BJT, and the base current. So this is the turn on transition. So here you have provided some base current. So from zero, it is rising like this. And then So when the BJT was off, it was blocking some amount of voltage because it was off. As soon as you provide the base current, the voltage starts dropping. It starts dropping, and simultaneously the current starts rising because you have provided the base current. So based on its beta value, the collector current will rise. So first there will be some surge and then it will settle to the load value, right? So this will be the current, collector current that is coming here. Okay. So you see there is some power loss which we call the switching loss. So you have some voltage, you have some current, there is some overlap of voltage and current. Obviously there will be some power loss, right? Due to the overlap of device voltage and device current. So this is the power loss. If you multiply each point,
मैं किसी का फेस वैल्यू पे लेता नहीं हूँ बट मुझे भी
The way like मेरे को
sorry, can you please mute?
सॉरी मैम
Yeah, so basically, if you just multiply each point voltage and current, so you will get this kind of curve. This is in the turn on transition. Now the point is you need to minimize this loss because unless this loss is too large and you are switching this your switching frequencies in some a few kilohertz, like it may be 20 kilohertz, 30 kilohertz, or 50 kilohertz, or even more than that, then you can understand that how much loss you will have to incur. So the lesser this loss, the better will be your efficiency and better will be your thermal management. So if this loss is too high, so your heat sink selection will also be difficult because you need to dissipate this heat so that your device is okay. So the more the loss, you will face difficulty to dissipate that heat. You will have to your thermal management will be complex. It will be complicated. So now how we can reduce this power loss? We can so see here the difference is earlier we were providing this much base current, now we have increased the base current. So now this voltage drops at a faster rate compared to this case. Now it drops at a faster rate. So obviously the overlapping portion is lower than well, earlier case. So now your power loss also reduces because now this portion is less compared to the this one. And similarly, you can again you can give a base current something like this with some hump here and then it settles to a finite value. In that case, this the voltage drops even more drastically. The drop is more sharp here, right? So the power loss is even lesser than case 2 here, right? So you if you provide this kind of a base current, then you can minimize this loss. You can make the you can reduce the loss. Okay. So all these three cases are for turn on transition. Similarly, for turn off transition, if you see, so this will be the opposite. So it was on. Now you need to go to off condition. So now it was carrying some current. That current needs to reduce. So as soon as you withdraw the base current, then it goes to negative and then it goes to zero. Why? Because you know there is a diode, right? Like we model this as a diode, the base to emitter here. We have a PN junction, right? So in the PN junction, some charge is stored. So when you are withdrawing the base current, the charge needs to be removed. The charge recombination needs to happen. So that's why first it goes to negative and then it goes to zero. So here the charge is getting recombined, right? After that only your current starts falling, your load current starts falling when the charge has become lesser. Okay. And this voltage has to increase because it will block some voltage in off condition. So this is the transition. Again, you will get some power loss here as similarly to on condition. Okay. So these are the dynamic waveforms for BJT. So this is the base current shape, right? That we already saw. First, there will be some hump, then uh, some stable current throughout the on condition, and then again when it is off, it will go to negative, then it will come to zero. Okay. So this, so some we have annotated this. So this is suppose I plus this peak value. This is IB on and this is IB minus. So these are some rough values, some like some empirical values usually used for design purposes. So IB on is usually twice IC by HFE set. So HFE set and beta, they are basically same beta. The parameter beta we studied, right? So that is the current amplification factor beta. So IB on is basically 2 times IC by HFE set, and IB plus this peak value 1.5 to 2 times of IB on. IB minus can be 1.5 times IB on in magnitude. So all these data you will also get in the lecture of Umanand sir. I have taken from there only. Yeah. So these are some values you can use while designing the drive circuit. Again, so now we were talking about this current. Now, what is the actual circuit? You will have to employ some circuit for providing the base current, right? So what is that circuit? The simplest form of the drive circuit for BJT is this with two resistors. So here some voltage will be there, some base voltage, some DC supply, and here there are two resistances, and here this is the base current. Now what will be the values of R1 and R2? How do you find? You can find via these equations. Okay. So basically your R2 is VBE set by IB on. So R2 is designed so that it can carry a current equal to IB on, this current. And VBE set is basically this voltage, this drop, base to emitter drop here. And IB on we already saw that in the previous slide we can express it like this. So here you will get R2 value and what will be R1 value. So here your voltage is VB and at this point your potential is VB set, right, with respect to ground. So and here you are getting
So,
IB on.
ma'am,
Yes.
ma'am, am I audible?
Yes, tell.
Ma'am, what is the difference between IB sat and IB on?
IB sat is not there. Where is IB sat? There is
No,
here
they
there
are,
is no IB sat, right? Where are you talking about?
ma'am, generally I am asking.
No, there is no IB set as such. There is VCE set. So if you see for a BJT, this. So if you see, we define a parameter which is VCE, which is basically the voltage drop across the BJT. So we define VCE set. When the device is on, there is some voltage drop across the BJT, which we call VCE set. Okay. But there is no IB set. There is HFE set or beta set, which is the amplification factor. Okay. But there is no IB set as such. Okay. There is this load current, collector current, base current, and emitter current. That's it. So, yeah,
Okay,
so
ma'am.
what I was talking is, yeah, so R1 value. R1 value is, so here you know what is the potential here, you know what is the potential here. So you need to simply find out, and the current here is 2 IB on. Basically, this is IB on, and through here also we have designed it so that the current is IB on here. So the total current in this branch is 2 IB on. So that's how we can find out what is R1 value. Okay. So yeah, this is the simplest form, and there are some more advanced circuits that we will see. in the later slides. Yeah. So basically, this I guess this will you will not need for numericals, but this is how practically the circuit is implemented. So this is the base. Here, this is the R1 resistor, and this is one IC TL494. This is basically employed to provide the gate the pulse, right? The base like high or low, something like this. When it is high, then base current we will provide here, and when it is low, then there will be no base current. Okay. So the operation of this one, you can refer to the lecture series. I will just tell it briefly. So here there is a potentiometer which basically is used to control the duty, right? And 2 and 3, so they are shorted. So basically this is a basically error amplifier, but here they are shorted. So this is a voltage follower. This portion acts as a voltage follower. And these three pins are not currently, like for this application, these three are not used, so they are grounded. And they are and here we have RT and CT, one resistor and one capacitor, right? So these values are selected so that we can so based on these values we can select this uh, on and off durations here. And here there are two internal switches, right? So when this one is on, you can see that current can flow in this way. So here current can flow like this in this path via this switch and then to the ground. Okay. This ground and this ground, they are same. The supply ground and this ground. Okay. So current can flow in this path through this and then to the ground. Okay. So these two devices are there for the based on their on and off condition, the base current will flow, or the path can be opened or the path can be short. Okay, for the base current to flow. And this is a typical buck converter. So yeah, so this you can take as an example. Okay. This is for practical implementation basically. If you want to practically design a circuit, you will have to use all these components for making the circuit.
Excuse me, ma'am.
Yes.
Ma'am, why RT and CT are called as precision components?
Precision components because actually if you the way you select the RT and CT values, based on that your this transition will happen, right? So basically, I am not sure why they are called precision components, but you will have to design the RT and CT value in a way so that you can dictate what will be your on time and off time. Okay. So maybe because they are called precision components because their values will have to be like very precise so that you can control the transitions, right? I am not sure why exactly they are called precision components. I will have to see. Okay, if I find the answer, I will tell you. But yeah, so
Okay, ma'am.
okay. So next we have this multi-stage base drive. So till this point we were only seeing two resistances in the base drive circuit, but now you can see there are multiple stages, right? Here we have R2, R1, and this current here it is again connected to a PNP PNP switch, right? So basically, this is our main switch. This is our main switch which we need to control. And here, all these portions, so this switch, all these switches are part of the base drive circuit. Here there is a PNP circuit. Again, there is a NPN transistor. right? And you can also have several mode based on your requirement. So why do you need this multi-stage base drive circuit? Because suppose you want a particular amount of base current to flow here, but your source here, you are connecting some source, so this source can't give this amount of current. It is not capable of uh, sourcing this amount of current. So what will you do? You will use this multi-stage circuit. What will do is eventually, if you see, the current drawn from this source will be very small, but anyway you will here get your required amount. Even though you are drawing very small current here, you will get your required amount of base current here because of this multi-stage circuit. So what will happen is, basically here, if you need certain amount of IB current, base current IB, so that current will come from where? That current will come from here, right? Through this circuit, because this is the only path. So you see, the collector current of this PNP transistor is basically the base current of this transistor. So for this PNP transistor to be on, it needs again some base current, right? So this is a PNP transistor, so the base current direction will be like this. When this base current will flow, this base current will flow only when this transistor is on, right? This transistor is on. So again, the collector current of like this current, some current will flow here and some current, and it will come like this. So unless this is on, there will be no path for the current, right? For to flow in this direction. If this is on, then the current can flow like this. And at each stage, you see the current is getting divided by beta. So if this is IB, so the base current of this will be this current divided by its beta. Again, the base current of this will be this current by beta. So actually what current you need to draw from here, it will be much less than your actual current requirement. So that's why this multi-stage circuit is used, so that we will have to source very less current for the base drive from the source. Okay. Yeah. So here there is this. This is again a multi-stage circuit, and here you see in here, along with the R2 there is an inductor, right? So the inductor here is present to make the turn off transition faster. So you see, when you need to turn off this, so we saw that the base charge needs to be recombined. The base charge needs to be removed, then only it can block the voltage across it and it can go to off condition. So then the current will flow like this. Okay. So a negative current will flow. So suppose some base current was flowing when it was on in this direction, right? In this direction, like this. Sorry, I'm wrong. Yeah. So the base current was flowing like this in this direction. Okay. So now what needs to be done is, so the current direction is suppose like this. Okay. Now
Excuse
when
me,
it, yes.
ma'am, why does the source can't be able to provide required current?
Mm, it can provide, but you will have to select a source which can source a very high amount of current. So if you can modify the circuit so that you don't need to draw very high current from the source, it is better, right? Because if you don't use this multi-stage circuit, suppose directly you use this circuit without any multi-stage thing, directly a source and then these two resistors, then you need to select a source whose current rating is quite high, right? Current rating, then its power rating should also be high. If we suppose I am assuming the voltage is fixed, then for higher current rating, its power rating will be high and then it will be very expensive, right? So if you just and compared to this power source, this extra BJTs, there will be this cost will be nothing, like this BJT and resistor. So if you can use a source whose current rating is less and power rating is less, and then also you can serve your purpose, then why not? Then why to use a voltage source with high current rating? You
Oh, okay,
understood,
okay. That,
right? This is just like just for your in terms of economical reason, and also like this is a very convenient method, right? So that's why. So it you will be underutilizing if you just use this like with a very high current rating, it is not required. So instead of that, you can use this circuit to get the base current. Yeah. So what I was telling is when it will turn off, then the inductor, so inductor will try to maintain the same current, right? Because that is the property of inductor. It doesn't allow sudden change of current through this, right? So what will happen is the current, so some amount of current was flowing through the inductor when it was on. So it will try to maintain the same current and the voltage across the inductor will reverse. If earlier it was plus and minus, it will reverse now because now you have withdrawn the base current, right? So in that way, you can make the process faster. The turn off process you can make faster and you can incur lesser amount of loss. So that's why this inductor is sometimes connected. And there are some other methods also. So instead of the inductor, you can also connect a minus V. So a negative source you can connect like this. Means like it will be connecting a voltage source in this polarity, right? Like this way. So the negative terminal will be connected here. In this way also you can make the process faster, right? You will the current will be synced in this here, like this, from here to here. Okay, so these are some of the methods. Yeah, and there is this circuit also. So here, if you see these portions, right? These portions, and here, if you see, there is some new circuit here. So this circuit is called the totem pole circuit. Okay. So here there is a NPN BJT. Then again there is a PNP BJT connected in this fashion. This configuration is called totem pole. This is a very popular configuration for providing for designing drive circuits. Okay, they are very widely used. This totem pole configuration. Okay, so after this configuration, we have this circuit, some RC circuit here, and in parallel with the RC there is another R, and after that we have the base here connected, right? So what is the objective here? The objective is again to make the transitions faster, so that we don't have to, so that we can reduce the switching loss, right? So you see, if we want to inject the base current like this, so that this BJT turns on, Q1 needs to be on, right? Unless Q1 is on, the current will not flow in this path. So when Q1 is on, we can provide the base current. And how the current will flow? Suppose when Q1 is on, then the current have two parallel paths through the RC and through this R1. But we know from like initially, just the moment the Q1 is on, this capacitor will act as a short circuit, right? So it will draw a very peaky current initially, and then the current will fall gradually. We you know, right, what is how the RC circuit behaves for a step change. So when this Q1 is on, some step voltage comes here. And when you present the RC circuit with a step change, the current is like this. Initially, there is a high current, and then the current reduces exponentially and settle, and eventually in the steady state it becomes zero. Why? Because now the capacitor has charged to this VCC value, right? So now this is open. It will not allow any current. So this path is open. Now the entire current will flow through this R1 resistance. Okay. So this will be the path. So yeah, so that's what I was explaining. It is explained here. So yeah, I think just a minute. I think this is the correct thing, or yeah, so actually this is yeah. So this is, yeah, sorry, this is the path. Yeah. And the next one, this is the off path basically. This is during on when Q1 is on and you are providing the base current. And in this picture actually, what you are seeing is when you are withdrawing the base current, then this capacitor will discharge. And what will be the discharge path? The discharge path will be through Q2. So the current will flow like this, and then back from here. So uh, this will be the discharging path from here to here, then through Q2. At that time, Q2 will be on, and from here back to here, right? So this is start during on, and this is during off transition. And if you are using this circuit, then your transitions become faster if you provide RC circuit instead of only resistance. Okay. So yeah. See, this is the current. So during on condition, the capacitor gets charged, and then the current settles here, and then the current flows through R1. What I was telling, the current flows through R1 in this circuit. Okay. And then when you are trying to turn off the BJT, then again there will be some negative current because now the capacitor is discharging in this way, in the opposite direction, and then it becomes zero. Okay. Because initially it draws a very high peaky current, that's why the duration becomes smaller. The larger this duration, the larger time you will take to make it zero, the loss will be more. So the faster you can make this current to zero, the base current, then your transitions will be faster. Okay. And these are some equations by which you can find out the value of R1, R2, and tau. Okay. Tau is the time constant, R2C, the time constant. Okay. So this is this is R2, this is C. And
Excuse me, ma'am.
yes.
Why R2 is less than R1?
Because if you make R2 very high, then your time constant will be high, and then this duration will also be high, right? Because this capacitor is getting charged through this R2. So higher the R2, higher will be the charging time or the discharging time, and then you will no longer get the benefit of faster transition. The purpose of adding this extra circuit is to get faster transition, right? So that your turn on duration and turn off duration are less, and you get less, like your loss is reduced. But if you make this R2 very high, then the purpose is lost, because now the capacitor will take long time to get charged and long time to get discharged. So that's why R2 will keep small, right? And R1 is higher than R2 because at some point of time this whole current, this total IB on flows through R1, right? So that's why you will have to make the R1 value higher so that your this current is not too high. Okay. So this voltage divided by this R1, this current has to be less, right? It shouldn't exceed the rating of this device. So that's why the R1 value is higher than this R2 value. R2 value need not be higher because the purpose of R2 is basically to charge the capacitor or give a discharging path to the capacitor, right? That's why. You understood, right? Because once this capacitor is charged, there is no current through R2. When the capacitor is fully charged, then the entire current flows through R1.
Okay, ma'am.
So if you don't provide some R2, then the current will be too peaky. It will be too high, and it can damage the. It can draw very high amount of current. So you can't really charge a capacitor directly from a supply. You will have to provide some resistance in the path. That's why we provide this R2 value. Okay, so yeah. Now, usually what we do is when we supply the base drive, there is some isolation from the signal side to the between the signal side and the power side. If you see any gate drive circuit for MOSFET or any base drive circuit for BJT, usually there is some isolation. We don't like here. I have shown this ground and this ground, they are equal, they are same, but usually that is not the case. There is always some isolation, and that isolation can be provided by put by using an isolation transformer like this, or we can use optocouplers. It can be optical isolation or it can be uh, transformer isolation through a transformer, right? So here we have used this transformer, and afterwards we have this diode and this circuit. And here we have optocoupler. So this is a photodiode. When it emits some photon, then this transistor will be on. And if this transistor is on, then there will be some current here like this through this transistor. And if there is some current here, then this will be on. If this is on, then this transistor will get its base current. And if this transistor is on, then again here some current will be there. So you can trace the path, right? The same I explained earlier. If this is on, then again here there is some base current here. Okay. So if there is base current here, this is on, and it will provide base current to this main transistor, right? So that's how we can give isolation via this optocoupler. Okay. Okay. What else? Yeah. So now we will go to MOSFET drive circuit. Till this point we were discussing BJT, and now we will discuss about MOSFET gate drive circuit. So what is the fundamental difference? The fundamental difference is BJT is a current control device. So during this whole condition, during this whole time, when the BJT is on, you will have to provide some base current. The base current can't be zero when this BJT is on. Contrary to this, you don't have to provide continuous gate current when the MOSFET is on. You will have to provide some gate current when the transition is happening. but afterwards your gate current becomes 0. Okay. So only during the transitions there will be some gate current. Afterwards you can make the current 0, but your gate to source voltage will have to be high obviously, but there will be no current here. Okay. So this is the fundamental difference. This is the waveform. So what I was saying that this is the current versus T. So the area under the current curve is charge. This we call the gate charge. So this is the gate charge. This is on transition. This is off transition. You can, the shape can be like this, and usually it is like this. Why? Because this is again an RC circuit. So there will be some resistance here, and it eventually becomes an RC circuit. So that's why the current shape is usually like this. Initially a high current and then exponentially decaying like this, and it is 0 here uh, when the MOSFET is on. Okay. So yeah. So if you just see this circuit, so this is the gate current and this is the gate charge again. And this is the simplest form of circuit, some resistor here. And here, this is this gate to source capacitor. So you need to charge this capacitor. When you want the MOSFET to be on, you need to charge this capacitor. So this is obviously an RC circuit, you can understand. Current will flow like this and it will charge the capacitor. And when this capacitor is charged, then you don't need to provide any current here. So there will be no current and your MOSFET will be on. Right. This is the peak current Ig plus. And then this is suppose the average current. If you average this becomes some Ig average value. So what is your gate charge? Gate charge is your Ig average multiplied by the on time. This is the on time. And you can also write Ig plus 2. So you can approximate it like a triangle like this. Instead of this exponential shape, you can approximate this as a triangle. So in that case, you can write half Ig plus times T on, because that will be the area under the triangle. So Ig plus is 2 Qg by T on, right? That is the expression for Ig plus, the peak gate current. Okay, this is the peak gate current. And what will be the gate resistance? The gate resistance value is Vg by Ig plus. So suppose this voltage here is Vg and the peak current here is Ig plus. So your R will be, gate resistance will be Vg divided by Ig plus. Okay. So was I muted? Did you hear the?
No, ma'am.
Yes, we could hear you, madam.
Okay, yeah. Yeah, so again the same problem. Suppose your source is not capable to give your required gate current during the on transition, then you can use some buffer circuits like this. So in that case, you can use multiple buffers in parallel, and then you can get high gate current from without having a very high current rated source. Okay. So this is the buffer circuit, and you can also use similar multi-stage circuit like we discussed in BJT. For BJT, you can use similar circuit for MOSFET as well. Okay. The totem pole circuit and then here this multi-stage circuit, the operation is same. Only thing is here, instead of base current, you will provide some gate current only during the transition period, not in the steady state period when it is on or off. Okay. Yeah. And then again you can use some isolated circuit, that is preferable. Why? Because if there is some surge, power surge, or some kind of disturbance in the power side, it shouldn't get transmitted to the signal side. So that's why it is preferable to have isolation in the drive circuits. So again, you can use optocoupler circuit like this, same as we discussed for BJT, or you can use this transformer based isolation. Okay, you can use this transformer based isolation from signal side to power side. So this was the topic in brief. Okay. The snubber circuit and overcurrent protection circuit we can discuss during the numerical solving time. So if you have any doubt, you can ask. Otherwise, we can take a small break of 5 minutes and we can come back.
Excuse me, ma'am.
Yes.
Ma'am, in the base type circuit where rectifier is involved, there are power side and control side.
Sorry.
The base multi-stage base drive circuit, there is a
Yes.
circuit involving rectifier.
Uh, multi-stage. Okay. Where is the rectifier?
Rectifier, ma'am, you have not covered, although in the lecture it was present.
Okay. So basically, I think you are talking about this. So here, after the AC circuit, after this AC, there was this rectifier, diode bridge rectifier, and then actually, I think in this side there was this transformer isolation, and then there were this.
Yes,
Here
ma'am.
there was one diode bridge rectifier which was providing for the power circuit, and again there was another winding which was providing, and then again one rectifier circuit which was providing for the control circuit. So this is DBR1, DBR1, and it will be DBR2. Yeah, in this way also you can provide isolation. This is also possible. So you can have multiple DBR circuits, and because they are already isolated by this transformer, so here you can give this supply to the power side, and this supply you can provide to the control side. Like that also you can have isolation. Yes. So you can see the lecture
Oh,
actually there. You will see this circuit.
okay.
Okay. So any other confusion? Any other doubt?
And it took a very long time to analyze which switch is on and which switch is off and how it affects the overall circuit and analyzing the circuit multi-stage.
You are talking about the multi-stage circuit.
Yes, ma'am.
Okay, so actually, see, this is not very difficult. Okay, you just sit once and like very calmly, you just analyze it. This is not difficult at all. Okay, so you just go step by step. So, what is your objective? Your objective is to have some base current here, right? Sorry, for MOSFET here, so gate current. Or if this was BJT, then base current, whatever it is. So, you need to have some current here, right? Now, how this current will come? This current will come only when this path is this BJT is on, right? Otherwise, how will sorry the only when this upper BJT is on, right? Q1 is on, because otherwise there is no path only, right? here there is some supply voltage, some VCC, suppose this here it is. So how will this supply give you some current if this path is open? There will be some closed path for the current to flow. So that's why this BJT has to be on, right? The current will flow like this. You understood, right? This is very simple from here to here. And when this BJT will on, only when it will get some base current. So there will have to be some base current in this manner. And note here that this BJT and this BJT, they cannot be on simultaneously. Otherwise, this you are shorting the supply. So if both of them are on, then this VCC is directly short to ground, and it is catastrophic, right? So the either this BJT will be on or this BJT will be on. They will never be on simultaneously. So now when this Q1 is on, Q1 will be on when it will get some base current. How this base current will come? Through this path. Through this path it will come. And how will this come? It will only come when this is on. This path is on, right? Through this path, this base current will come. And when this will be on, when there will be some base current here. This is the same thing. The same logic applies everywhere. So its base current will come from where? Its base current will come here like this. When this transistor is on, then only this base current can flow like this in this direction. And when this will be on, when it will get some base current again. So this is kind of a like step by step. If you analyze, this is very simple. Okay. So you just go, you just start here, and eventually you come here, then here, then here. You will understand how this path is, which will be on, which will be off. Okay.
Sure. Thank you, ma'am.
Yeah. Okay, so let's take now it is 7. So at 7:05, I will come back. Okay. Then we will start the numericals. Okay. Let's start the numericals then. See the first problem. The first problem is about the MOSFET gate driver. So a converter switch gets driven by a gate driver circuit as shown in the figure below with the following specification. So VDC, this VDC value is given 48 volt. RL is 50 ohms. This is RL. And MOSFET switch, so they have specified which switch IRF 740. VC SAT is zero point 0.2 volt. So VC SAT 0.2 volt for Q1, Q2 and Q3. So for these three BJTs, the VC SAT is given. Okay. By considering the maximum turn on time T on as 1 microsecond, calculate the value of gate resistance RG. So you need to find what is the RG value here, right? Okay, let's see how we can do that. So you understand here that when Q2 will be on, then only there will be some current here. So Q2 has to be on here, right? From the supply, if we need to have some current, so Q2 will be on. Okay, see here. So for that we need some data, right? So I have taken this data from the data sheet of this IRF 740. This if you search this, you will get, this is from Vishay, the manufacturer. So from the data sheet you will get all this data. Okay, but you will have to understand which data you need for a particular question. So here we need the gate charge. See here QG, this is gate charge. QG max is basically 63 nanocoulomb. It is specified. This is the maximum gate charge, right? So we already saw, like when we were discussing the circuit for MOSFET gate driver, we saw that the gate current is something like this, right? Like this. This is during on and this is during off, right? Exponential decay due to RC charging circuit. This is R and here there will be C. So if this was Ig plus, if you remember, we denoted it as the peak current as Ig plus, right? So this was the peak current and Qg was the gate current, gate charge is Qg was Ig average times Ig average times T on, right? Ig average times T on. Now T on they have specified the maximum turn on duration, they have specified as 1 micro, right? Now you need Ig average. What is Ig average? Ig average is Ig peak by 2 approximately. So we can find what is Ig plus. Ig plus is 2 Qg by T on, right? So from this equation, this is Ig plus by 2. So Ig plus is 2 Qg by T on. So we know Qg, we know T on. From there we get 126 milliampere. Now if you apply KVL in this loop, if you apply KVL here, so from VCC, if you trace the path from VCC through Q2, through this path, the current is going. Okay. Just at the moment when you uh, are turning this on, when you are giving the gate pulse, at that time the KVL will be VCC minus VCQ2. So the turn on volt, the VC set of Q2 minus IGRG, that is equal to 0, because at that time capacitor is not charged. You have just given the supply here, so that's why it is 0. So from here you know VCC, it is given, VCQ2 is given, Ig value you just found out. you need to find Rg. So this comes out to be 117.46 ohm. Okay, this is the gate resistance. Fine. Okay. So let's see the next part. So in the next part, they are asking that for the driver circuit used in question 1, which one of the following response is correct? For the same, find the magnitude of V out, V naught across the load resistance RL by considering the high duration of pulse is 0.6 TS. Assume the drop across the switch is negligible. So what additional data they have given? The pulse on duration. So these are the two responses. This is response 1, this is response 2. So this pulse duration, high duration is what? 0.6 TS. If this is the total time period, if this is the total time period TS, then the pulse high duration, this duration is 0.6 TS. Okay. And they are asking, they are saying that the drop across the MOSFET is negligible. So which of this response is correct one? Okay, which will be correct? There are 4 options here. So first of all, you see that, okay, first of all, we will not see the solution. We will try to see how we can come to the solution logically. Okay. See here, if you see this circuit here, so we know when Q2 is on, we can get the gate drive current, right? Via Q2. Now, how Q2 will be on? When there will be some base current here, right? From where this base current of Q2 will come? The base current of Q2 will come via this switch. From here. From this switch, the base current will come. This is a PNP BJT. PNP. So for PNP BJT, the base current direction is like this. Okay. So the current comes like this, and then the emitter current gets divided between base current and collector current, right? For PNP. So if the base current has to be there for Q1, then this point will has to be low. You see, if this point is high, like this here, then there will be no base current, because then it will try to push current in this direction, right? But it can't push current otherwise, so the current base current direction has to be this. So when this is low, then only Q1 will be on. And unless Q1 is on, Q2 cannot be on. So when this pulse is low, then only you will get base drive the gate current here. Did you understand why? Because for the current to be like this potential will has to be, this pulse has to be low here. Otherwise, current can flow from here to here, because current always flows from higher potential towards lower potential. So if this is low, then only this base current will flow like this. So that's why during this condition only you will get base current, and when this is high, your there will be no base sorry, not base current, gate current. So you will not this MOSFET will not be on. Okay. So then we have already found out one answer. So our response 2 is the correct one. You understood, right? Because when your pulse is low, then your V naught will be high, and when your pulse is high, your V naught will be low. So when your pulse is, you are giving gate pulse here, then the MOSFET is on, it is on, and then the current will flow like this. Sorry, the current direction I drew opposite. The current will flow from the source like this through the MOSFET, right? Like this. So when there is current, there will be some voltage drop across this load resistor. And when the MOSFET is off, then there is no current path because this is open. There will be no current through the resistor and there will be no voltage drop. Right. So when this is low, you will get some voltage across RL because the MOSFET is on. And when this is high, the MOSFET is off. That's why you will get no output voltage. Right. So this is the correct response. Now you have correct response. So the response 2 is given in B and in D. So among these two, B and D, which one is correct? That we will see. So yeah, so that's what I have written, which I explained you that when uh, Q1 is on, then only you will get the gate current here. And here they specified that this high pulse duration is 0.6 ts. So the rest of the duration is 0.4 ts, right? So the duty is here 0.4. So the average value of this V out will be what? This source voltage VDC times duty, right? Because that is the average voltage here. So this is 0.4 times 48. So 19.2 volt. The correct option is option D, 19.2 volt. You understood, right? How we got to the solution? Okay. So I hope the explanation is clear. Let's see the next problem. Yeah. So what is the maximum value of switching frequency that can be used for MOSFET? For the question 1. So there the duration was 0.4 ts when the MOSFET was on. The on duration was 0.4 ts, and they specified that the turn on duration was 1 microsecond, right? So from here you can get the total time period, which is 2.5 microsecond. Okay. So from here you can get the switching frequency, which is 1 by ts, that is 400 kilohertz. Okay. So this has been this we have done based on the given data. Okay. So this comes out 400 kilohertz. If the load resistance in question 1 is replaced by an inductive load which draws 10 ampere current from the input DC source, calculate the shunt snubber capacitor. Okay. So now there is some new thing. Calculate the shunt snubber capacitor. What is snubber capacitance? That we will see. Okay. So what they are saying is they are saying that here there was a resistance. Now instead of some resistance, you have an inductive load. So there is some resistance, and along with that there is some inductance. Okay. So this is the load now, some RL load, and it is drawing. It is an inductive load and it is drawing a 10 ampere current from the input DC source. Okay. First, I will explain what is a snubber circuit and why it is required. Then I will solve this problem. So here it is shown for BJT. Similar logic we can apply for MOSFET also. So suppose there is this BJT, okay, and here there is some inductance. So this inductance, here they have specified some inductive load, but even though your load is purely resistive, then also there could be some inductance from the traces, right? So if you design a circuit, there will be some wear or some trace for the PCB. So in the PCB, you will definitely get some parasitic inductances, right? Like this. And you have this device. So practically, if you see, there will be some leads. there will be some leads of the device. So if this is your practical device, suppose, okay, and these will be the leads. For BJT, some collector, emitter, and base, and for MOSFET, there will be gate, drain, and source. So here also some parasitic inductances will be there in due to the leads, right? So you can't avoid to have some inductance here. There will be definitely some inductance. Uh, there will be some inductance, right? Now, what happens when you turn off this device? Suppose so some current was flowing, in the, so now you don't see this part, you don't see this diode, this resistor, this capacitance. you just you just focus here. Don't suppose this is not here now. You just see this part, only the inductance is there and this device is there. So some current was flowing. Now you have turned off this device, okay? So now the inductance doesn't have any path to flow. The inductance current is can't flow anywhere because this is open now. So due to the sudden interruption of the current, there will be some LDI by dt definitely, right? Because now the current will have some negative slope because you have interrupted the current path. So there will be some LDI by dt with very huge di by dt. Okay, very huge di by dt, and that's why this LDI by dt will also be large. Now, the device, the voltage across the device, usually what we see, the voltage across the device that the device blocks is the DC voltage, right? The supply voltage. But now, instead of the supply voltage, the device has to block a voltage which will be your VDC, the DC voltage plus this LDI by dt. If you apply KVL here, you will see. If you apply if this is your supply, suppose this is your supply here. If you apply KVL, you will see the voltage appearing across the device will be VDC plus LDI by dt, right? Now you don't have any control over this LDI by dt. Based on your turn off transition of this switch, this LDI by dt can vary. So this can be very large sometimes. If this is very large, this total quantity may exceed the voltage rating of the device and your device will blow off. Okay. Your device will be gone. So we can't let this happen. This LDI by dt you will have to eliminate. How will you eliminate? That's when this circuit comes. This extra components, this D, this R, this C. This is called a shunt snubber circuit. Also, this is called a RCD snubber. Okay. And also called a turn off snubber because this circuit is used during turn off condition, turn off transition. Okay. So how this prevents this LDI by dt? See, if you see here now, you have an extra path for the inductor current to flow. Even though you have turned this off, now the inductor current flow via this diode to this capacitor and it can charge this capacitor, right? So now the inductor current is not interrupted because you have provided an additional path. Now it can charge this capacitor through this diode, right? Like this. Like this, it will charge this capacitor. Okay. And then when again you will turn on, this MOSFET will be on, then the capacitor will get discharged via this R and through this MOSFET or BJT like this. Okay. Then it can discharge through this R and through this path. Okay. So this is called the RCD snubber or the shunt snubber. So here we can find out the equation. So here this IL current is basically the sum of IC, that is the collector current, or if you have MOSFET here, then it will be the drain current plus I cap, which is the capacitor current, right? If you apply KCL here, the This current is summation of these two currents. And what is IL? IL is what is IC? IC is IL times 1 minus T by TF, where TF is the fall time. So if you see this, if you find out the equation during this interval, the current equation is IL times 1 minus T by TF during this interval. I am talking about this interval, plus I cap. I cap is then what? I cap is this expression, and you can find out the voltage across the capacitance, which is integral I cap dt and 1 by C, like this, right? From 0 to TF. If you perform this, if you put the I cap expression, you can substitute I cap with this one, and you will get, and this is the initial condition, because at TF your VCE becomes VCC, right? So this, so at TF, this voltage across the capacitor is this supply voltage. So from there you can find out what should be your capacitance value. What should be the snubber capacitance value? It is ILTF by 2 VCC. Okay. This should be your capacitance value. Did you understand how this snubber circuit works?
Yes, ma'am. This diode and resistance is providing snubber. Is eliminating di by dt. Right?
Sorry, can you repeat?
This LDI by dt is eliminated or removed by diode and resistance addition. Right?
Yeah, the LDI by dt comes because you interrupted the inductor current. If this circuit was not there, there was no path for the inductor current to flow. And suddenly, if you interrupt the inductor current, then the current is reducing, suppose. Okay. So based on the slope of this current, you will get this di by dt. And if there is some di by dt, then there will be some voltage across this inductor. And this voltage plus this voltage comes across this device. Now, if you are not interrupting the current through the inductor, you are giving additional path, then there is no LDI by dt, because it is already getting path here through the capacitor, right? So then the switch is protected. Your device is protected, right? The LDI by dt doesn't come across this switch.
Got it.
Yeah. So we can also find out the expression for R. Yeah, so actually, so there they had asked the snubber capacitance value. So from this formula, you can directly get the capacitance value. So you know what is IL, because they specified 10 ampere current was flowing, and TF you can find out from the device data sheet. So it was 74 nanosecond. You can see the device data sheet. You will find out this. And VCC value was given already. So the capacitance value you can find out like that. Okay. So what is the next question? The gate resistance branch connected between point A and B in question 1 is replaced by the following combination. Find the value of capacitor if the turn on and turn off duration are considered same. So this is point A and point B. Earlier there was only this resistor. Now we are replacing the resistor by this circuit. So this one we already discussed. There is this RC circuit. Here for BJT we discussed this. There is this RC circuit, and in parallel there is another resistance. Okay. So we are using this circuit. They have asked the value of the capacitor C, and they have also told that turn on and turn off duration are considered same. Okay. So yeah. So if you see, so are this gate resistance value we already found out. when there was only this resistance, we found out 117 ohm. And turn on and turn off durations are same, so both of them are 1 microsecond we can take. Now, so the time constant here is Rg2C, right? This is the time constant. Usually the rule is 5 times time constant should be your turn on time, right? Because turn on duration. Why? Because uh, the time it takes to charge this capacitor fully. So if you fully charge this capacitor, then only uh, then only your MOSFET is fully turned on, right here. So then, when this capacitor is fully charged, then this path gets open and the current can flow through this, right? But here for MOSFET, we are talking about MOSFET. So you don't need the gate current throughout the on transition. You just need gate current for a very small duration. After that, the gate current is zero, right? So that's why this 5 Rg2G, see, this should be at least equal to your turn on duration, which is 1 microsecond, right? So that's how we can and what is Rg2 value? Rg1 by 5. We already saw the expressions, right? The design expressions. So Rg1 value, you can get Rg2, and then from this equation you can get the capacitor value here. Okay. So this circuit is used to shorten this duration, to make this duration smaller.
And this turn on equal to turn off is given.
In the question, it is specified that you can take the turn on and turn off durations are same. It is given in the question. Okay. So, yeah. So next question, consider a voltage source, inductor and a MOSFET in series. The inductor carries a continuous current of 1 ampere. So the inductor current IL is given 1 ampere. Calculate the instantaneous voltage across the MOSFET if it is suddenly turned off. The total fall time is the sum of turn off delay and fall time. Refer to datasheet of this. So another switch is given. Okay. So the same problem. If there is inductance, some LDIDT will come. Okay. So I have taken this data from the device datasheet. So this turn off delay time and fall time, they are given here. First, we need to find out what is the voltage across the MOSFET. So the voltages that we discussed, the supply voltage plus LDI by dt. So the fall time is 103 nanosecond. Di is what? The current. What was the current through the inductor? It was 1 ampere, right? And dt is the fall time, which is 103 nanosecond. Because this was the diagram, if you remember. This was the diagram. So we have approximated it as linear fall, but usually it is not linear fall anyway. So this is the fall time, right? So your slope di by dt is what? Current. So this current divided by the t fall, that is your slope, right? This current, this was 1 ampere, that is specified, this current, and this time duration is 103 nanoseconds. So di by dt is this value. And your switch voltage is like the voltage that is coming across the switch, that is supply voltage 50 volt plus this di by L di by dt. So L value was given. So if you do L di by dt, then you will get this value. So this is a very large value. Sorry. So you see, this is a very large value, right? So in the data sheet, you will see the voltage rating of the device is 200 volt. So you can understand if instantaneously, even though for very small duration, this voltage appears across the device will be gone. Okay. So the voltage rating is 200, and the voltage that is coming across the device, it is more than 1000 volt. So more than 5 times its rating. So the device will be blown. It will be damaged. So now obviously you will have to use some snubber circuit for this. So the next question is on snubber circuit. The MOSFET in question 6 requires a RC snubber for protection. Calculate the value of capacitance, minimum value of R and maximum value of R required for the snubber. Assume that the MOSFET is on for 20 microsecond, and again you can see the data sheet for the data you require. Okay. So yeah. See, here we already talked about how we can find the value of this capacitor, but we didn't talk about this resistance value. How we can find out this resistance value? So the resistance comes into play when the capacitor is discharging. So that's when it comes into play. And if you are not using this diode in parallel with the resistance, then during charging also this resistance will be in the circuit if this diode is not present. Okay. Anyway, so you see, so the capacitor discharges like this. Now, uh, now there is already an inductor current here, and the capacitor is also discharging, right? So this whole current VCC by R, the capacitor voltage is VCC. So VCC by R plus IL, this whole current will flow through the device. This current should be less than the device current rating, right? So this is one inequality. Another inequality is what? That this discharging duration should be less than the on time of the device. Okay. So T on minimum should be greater than 5 hours. Otherwise, the discharging will not be complete. If during the discharging process the MOSFET is off, then the discharging will not happen, right? Some voltage will remain here. Then in the next cycle, when again it is during turn off, it will not act properly, right? Because there is already some voltage. So before the next cycle, you will have to discharge the capacitor properly, so that when again you turn this off, then there is no voltage across the capacitor. Okay. So these are the two inequalities. From there you can find out this relation, and this is the minimum value and this is the maximum value. Okay. So I have used these equations here. So the minimum value and the maximum value uh, I have found out. Okay. From the inequality. So next question. Calculate the power rating of the resistance if the on time of the MOSFET is corresponds to duty ratio of 0.4. So what is the power rating of this resistance? So the stored energy in the capacitor is half CV square, where V is equal to VCC, this supply voltage. So half CV square, this is the energy. And if you multiply this with the operating frequency, the switching frequency, then you will get the power, right? Now, what is the duty? The duty ratio is 0.4. They have given the duty ratio is 0.4. So the on duration was 20 microsecond, and your duty is 0.4. So you can find out TS from here. This was 20 microsecond and this is 0.4. So Fs is the reciprocal of Ts, 20 kilohertz. So you have all the data. You have the C value, you have VCC value, you also have the frequency value. So you can find out what will be the power of this power rating of this resistance. Okay. So You understood, right? The snubber circuit and its operation and how we can find out the C and R values. Okay. So let's see the next problem. Just a moment. Yeah. So what is this? What is the problem? The problem is that overcurrent protection is applied for uh, just a moment. Yeah. So overcurrent protection is applied for this device IRF P260 MPBF MOSFET. The diode. So okay, I will explain how this circuit works. So see, so here we have this MOSFET, right? And suppose some current is flowing through the MOSFET, some ID current, okay? So you know for MOSFET, the voltage drop across the MOSFET during on condition, VDS on is what? VDS on is RDS on times ID, where RDS on is the on-state resistance of the MOSFET, okay? So times ID. So if so then this is a linear relation. If the current through the MOSFET increases, then the voltage drop across the MOSFET also increases, right? If we assume that RDS on is fixed, then as ID increases, VDS on increases. Now you see, suppose you want to limit the current up to a particular value, and after that value, if current further increases, then you want to withdraw the gate pulse so that the switch is off then, okay? So that is a protection feature. How will you do that? So now here if you see from this point, there this diode is connected like this, and here this is a comparator, okay? So this is the plus terminal, this is the minus terminal, and with the minus terminal some reference voltage is there. So this is some circuitry where we are getting some Vref, which is the reference voltage. How this comparator works, if V plus, if the voltage at the positive terminal is greater than V negative, then this comparator will be high, right? If the comparator is high, this is some circuit that I will discuss if I get time, but if this comparator becomes high, then actually what happens is this voltage here becomes high, okay? If this voltage becomes here high, then this BJT is turned off. If this BJT is turned off, then there is no gate pulse here. And then if you withdraw the gate pulse, the MOSFET becomes off and there is no current, okay? So for now, you don't see this circuit. You just assume this point is connected here. So if this point is high, this potential is high, and then this is a PNP transistor. So the base current has to flow like this. If this potential becomes high, then there is no base current here. So this BJT is open. This BJT is off, and the current can't flow like this. Current can't flow through this path, and if there is no current here, then there is no gate current also, and there is no gate pulse also, okay? So then your MOSFET will be off, okay? So how does this happen? See, if so here this point is connected like this. Now you see there is a current path through the diode through this MOSFET like this, okay, to the ground. And what is the potential of this point with respect to ground? The potential of this point is VDO, that is the drop across this diode, plus the drop across this MOSFET, right? This is the potential of at this point, sorry, at this point, at this V plus terminal. And the potential of this point is basically the drop across the MOSFET, right? So when this potential becomes greater than this potential, then only the comparator is high. Okay. So when your VDO, when this VDO plus VDS on is greater than the reference you can select based on your requirement. Based on at which current you want to turn off the MOSFET, you can select the VREF. When this is greater than VREF, then your comparator becomes high. Okay. So this is also called a desat protection, desaturation protection. Okay. This protection we implement for MOSFETs. Okay. And this circuit is there. You can see the explanation in more detail in the lecture. But briefly, if I say that, see, when the MOSFET was off, suppose the MOSFET is off, then it blocks some amount of voltage, right? Now, from when it is coming from off to on transition, so the voltage will fall, right? Now, if this is the logic that when the potential at this point is higher than this point, then it becomes high. But during this blocking period, the voltage is already too high, right? Because now the MOSFET is blocking the voltage across the MOSFET is what? This is the total DC voltage. This is very high voltage. So always it will see, okay, the potential at this point is always higher than this. So always this will be high and always this BJT will be off. So there will be no gate pulse at all. You can't turn on this circuit, the MOSFET at all, because it will always see a high voltage here and it will never make this low, right? Now, so during this transition, okay, so you will have to disable this circuit for some time so that it can transition from this high value to the low value, right? Then you can again enable the desat protection circuit. So when you are going from this to this, from off to on transition, then you can disable the circuit for some small time, and once it has already turned on, then you can enable this protection, because this desat protection is required when the MOSFET is on, when it is carrying some current, because this is basically overcurrent protection. You don't need it during this time. So that's why this circuit is the circuit is placed here, so that for during this duration you can disable this portion, and then after that again it will be you can enable this. Okay, that's why. Yeah, so this is the overcurrent protection circuit. In the question, they are asking that this just a minute. So what they are asking, so this D0, this diode, this is the combination of two diodes with 0.7 volt drop. Calculate the value of drain current for which when the circuit operates if VREF is 2 volt. So this voltage is 2 volt they have given. Okay. So this is now very easy. Your RDS on you can find out from the device datasheet. It is 0.04 ohm. And this, what is this potential? VDO plus VDS on, which is 2 times 0.7, because there are two diodes they have said. So 2 times 0.7 plus this RDS on times IDS. And this value is when this will be equal to 2 volt, then only this circuit will start operating, right? So from this boundary condition, you can find out what is the IDS, which is 15 ampere. Okay. If current reaches this value, then the circuit, the protection circuit will start operating. Okay. This is the current value.
Excuse me.
Tell.
Why you said boundary condition?
You are not audible.
Ma'am, why you said boundary condition?
Boundary condition because this is exactly equal the reference voltage. So that is the boundary condition. When this V plus is exactly equal to V minus, that is the boundary condition, right? And if it becomes greater than, slightly greater than this, then it will become high. So this is the boundary condition.
Okay.
Okay. So this question, this is a multiple choice question. Which of the following statements is true? So first one is gate drive power requirement for MOSFET is more than BJT because the former is a charge control device. The next option is gate drive power requirement for BJT is more than MOSFET because the former is a current control device. Gate drive power requirement is same for both MOSFET and BJT and none of the above. So which one is true? What do you think? Which one is true? From intuitively, which one can be true, you think?
B part.
Yeah, right? Because for BJT, you will have to constantly supply the base current. So obviously there the power loss is more, power requirement is more. But for MOSFET, you will have to provide the gate to source voltage, but there will be no current. There will be some current in the for a small duration. After that, the gate current becomes zero. So the power requirement is lesser for MOSFET than BJT. Option B is correct. Okay. Option B is correct. Yeah. So, so I think this was the last question. You just see the problems. These problems are very interesting problems actually, and you will require this for when you will design the gate driver in later stages, or like whether you may be designing now also, I don't know. But yeah, so this gate driver circuit, this is very important actually. For any circuit to operate, any converter to operate, you will have to learn this gate driver circuit. Okay. So if you have any doubt, we can discuss, or otherwise we can conclude today's session.
I have a doubt.
Sorry,
And how to revise all the previous lectures as designs approaching.
previous lectures. So I think after the 12th week, so this is the 11th week. In the next week, that will be the last week for this course. And then I will take one session where I will discuss problems from like the entire syllabus. We can discuss problems. Okay. So
Great.
that will be around, yeah, in the mid April. That will be, yeah, mid April. Like that. Okay.
Madam,
Okay.
how did you get 1 minus T by TF?
Okay. So I think you
Hmm?
were talking about this question, right? For the snubber circuit, right? You were talking.
Yes, yes.
Uh, just a minute. I will go there. Yeah. Right. So, yeah. So you see here, so this is the current. So this is the current waveform with respect to time, right? If you consider this interval during this fall time here, so what will be the equation? So here the current is IL, right? At this point, at the starting of this fall time, the current is IL. The value is IL, right? And this is a negative slope. Current is falling, so the slope is negative, right? And at the end of this duration, the current is zero, right? This much you understood.
Yes.
Then what is the slope? The slope m, if we denote the slope as m, then what is the m? M will be final minus initial. So final is 0, initial is IL, initial is IL divided by the time duration, that is TF, right? So that is my slope. Okay. So you just take this. If you suppose you have this straight line like this is your slope m. So what is the, if this is my y axis and this is my x axis, what is your equation? Your equation is y equal to, and if suppose this point is C, if like this y value is C when x is equal to 0, what is your equation? Your equation is minus mx plus C, right? You understood this? So when your x is 0, if you put x is equal to 0 here, you get C. So at x is equal to 0, your y value is C, and then there is this negative slope, that's why this is minus mx, right? So I have done the same thing here. So your slope is this minus IL by TF, and this value is IL. So the equation becomes IL minus IL by TF. IL by TF. Okay. And if you take IL common, then you will get this value IL into 1 minus T by TF. Okay. Sorry. Here it will be T. Uh, so IL T by TF. Right?
Y becomes C.
Sorry.
Y is equal to C.
At
Y is equal to C.
at x equal to 0, right? So I
Yeah.
am just talking about this portion, not this portion. So if you just take your your starting interval at this, so it is similar to this, right? You take this instant as your initial instant. This is your t equal to 0, and this is equal your t equal to tf at this point. So it will be like this, right? The equation.
Yes. Yes.
Mm. Okay.
And what happens if all capacitor charges flow through MOSFET or transistor?
Capacitor current flows through the MOSFET actually. When it
Uh,
is discharging, it is flowing through this R and then through this MOSFET. This is the current path.
yes. If is there any damage to MOSFET?
There will be damage in MOSFET if the current is higher than it can withstand. So the MOSFET has some certain current rating, certain voltage rating. If you see the data sheet of a MOSFET, there will be some continuous current rating, some pulsed current rating. So if that current exceeds that value, then the MOSFET will be damaged. So that's why we got this. That's why we got this inequality here at the first place. This inequality came from this criteria only, that this current should be less than the device current. This IL current plus the current that is coming from the capacitor, the summation should be lesser than the device current rating. So that's where we got the minimum resistance value, right, from here. So R should be at least R should be greater than or equal to this value.
And the time 1/6 time, how did you get?
1/6? No, this is
No, not
5C. This is 5C, not 6. This
not
5
here.
is
One.
because, sorry.
Okay. Yes. 5 is because.
Yeah, so 5 is basically, so if your time constant is RC, then 5 RC is typically is the time when the capacitor takes to fully charge. So the typical charging time is 5 RC, 5 times the time constant. Okay. So I don't know if you have studied the the behavior of RC circuit, RL circuit, all these things. So
Yes.
if you have studied it, you will see that the time taken typically to charge the capacitor, that is 5 RC. Okay, if RCU is
Yes.
your time constant. Yeah.
Yes. And one more problem you told,
Yeah.
1/6 time. 1/6
One
time.
1/6 time where
Uh,
uh,
Before problem. One by
one
six pulse.
first problem.
Yes.
Where
1/6 time first. Not this. Next. Yes. Point 6 TS. What is
so
that point?
this is the time duration when this pulse is high. So if just so this is the total time period, right? This is the total time period, TS. So the time when this pulse is high, this time is specified 0.6 TS. So 60% of the total time period, the pulse is high, and rest of the 40%, the pulse is low. This is 0.6 TS. 6 TS. Okay. This
Then
this is the
why did
time.
you take? Then why did you take duty ratio 0.4?
Because I explained, right, that when this pulse is high, then this circuit, this MOSFET is off. When this pulse is high means the potential at this point is high. This
Oh,
is the V pulse. Okay.
yes.
When this V pulse is high, then this MOSFET is, this BJT is off, because this is a PNP BJT. So if this potential is high, the base current will not flow. For the base current to flow, this potential has to be low. That's why the duty is complementary to this pulse. If when this pulse is high, the MOSFET is off. When the pulse is low, the MOSFET is on. Okay.
Yes. Thank you.
Yeah. So any other doubt? Mm. Okay, so let's conclude today's session. I shall stop the recording. Okay.